calculus is also useful for developing good numerical methods. A very useful numerical method is called Newton's method. And Newton's method is a method of root finding. And root finding is a method of solving the equation f of x equals 0 for x. X is called a root of the function f. So the idea of Newton's method is that you have a graph of y equals f of x, and you have some guess for the root. Let's call that x sub n here. This may be the nth iteration of Newton's method, so we'll just say x sub n. The function value here is f of x sub n. We draw the tangent line to the curve at that point. The slope of the tangent line we can get from the derivative of the function. And we see where the line intersects the x-axis. The point of intersection then will be our next guess for the root. So xn plus 1 is supposed to be a better guess for the root, which lies slightly ahead of the intersection of the line with the x-axis. So it's the next guess for the root after the previous guess, which was x sub n. So in order to construct the numerical method, we need to first write the equation for the line. So let's x, y represent a point on the line, then y minus f of x n. So the difference between the point on the line and f at xn is equal to the slope of the tangent line, so f prime of xn, times the difference between the point x on the line and x sub n. So this is just a simple equation of delta y divided by delta x is equal to the slope, the equation for the line. So to construct Newton's method, then, we want to figure out where y is equal to 0 is at this point. So for Newton's method, we want y equal to 0. And then x then is going to be our next value. So then x will be xn plus 1. We substitute into into this equation for the line, and we have minus f of x sub n is equal to f prime of x sub n times x sub n plus 1 minus x sub n. And from here we can get Newton's method. So we solve this equation, which is linear in x sub n plus 1. So we can solve this for x sub n plus 1, and we get x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. And this is called Newton's method. Okay, so this is an iteration method. You need to start with an initial guess for the root. We typically call that x sub 0. And then we plug in x sub 0 and we can get x sub 1. Then we plug in x sub 1 and we can get x sub 2. And we do that until we're happy with the convergence to the root. So we can look at an example. We can estimate the square root of 2. What is the square root of 2? So the square root of 2, so we can see what how our estimate will do. The square root of 2 is approximately 1.41421. Okay, so let's see how Newton's method will do. We need our f of x for square root of 2. So square root of 2 is supposed to be a root of f of x. So we know that if we take f of x equals x squared minus 2, then if you plug in x equals square root of 2, you get 0. So square root of 2 is one of the roots. The other one is negative square root of 2. So we're aiming to get the positive root. Here we take the derivative. We get 2x using the power rule. And then we need, we can plug it into the Newton's formula. So what do we get here? We get x sub n plus 1 is equal to x sub n minus f of x sub n, so that would be x sub n squared minus 2 divided by 2 times x sub n. In a computer, you would use this form, but in a hand calculation, I'm going to combine it into a single fraction. So we multiply numerator and denominator by 2xn. So we'll have 2xn squared minus xn squared, which will be xn squared minus 2 is plus 2 divided by 2xn. So I can use that for my hand calculation. We need an initial guess for the root, so we'll just choose an easy one, which is an initial guess of 1. Okay, let's have a look at the iteration then. What would be x sub 1? So now we're looking at n equals 0. So we have x sub 1 is going to be x sub naught squared, which is 1 squared. So 1 plus 2 divided by 2 times 1 divided by 2. So that's the fraction 3/2, which is just 1.5. Okay, so we went from 1 to 1.5. So actually we're getting a little bit closer to square root of 2. The next iteration would be x sub 2. So x sub 2 would be what we would put in x sub 1 here. So it's 3/2 squared, that's 9/4, plus 2 divided by 2 times x1. 2 times 3/2 is 3. And then if you put this under a common denominator and add it, we would get 17/12. Which works out to 1.41667. So from 1.5, we move to 1.41667. And the root is 1.41421. So we already got accuracy to 2 decimal places. I'll do one more before it becomes too painful. So x3 then will be x2 squared. So it's 17/12 squared. Plus 2 divided by 2 times 17/12, which is 17/6. Okay, that's a fraction. That's a fraction equal to 577/408. And if we write the decimal for that, that would be 1.41426. So now we're getting accuracy to 4 decimal places. So the next one will be x4 will be extremely accurate. Newton's method converges very fast. In fact, it's the fastest converging root finding method. The only difficulty of Newton's method is you need to find analytically the derivative of the function. So let me summarize. Newton's method then applies calculus to find the root of a function. The way it applies calculus is it allows you to find calculus allows you to find the slope of the tangent line to the curve, from which you can construct a formula for the tangent line, and from which you can construct the point that the tangent line intersects the x-axis. And that enables you then to construct an iteration routine. The iteration algorithm is xn plus 1 equals xn minus f of xn divided by f prime of xn. All you need to get this going is a good initial guess, x naught. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.